Okay, so good morning again to everybody. We have arrived at the end of this course. In this last lesson, we will conclude the discussion of the Sommerfeld-Half space problem that we introduced in the previous lesson. And the course will be ended by an interesting seminar by my colleague Walter Fuscaldo, whom I will present to you later. If you remember, in the last lesson, we introduced the configuration studied by Sommerfeld, that is a perfectly conducting half plane. What we will do today is to generalize that discussion to the case of an impedance change the boundary condition that holds on the infinitesimal within half plane. In the previous lesson, in particular, we discussed two solutions to the problem when the half plane is perfectly conducting. First, the elementary solution proposed by Gori in the 1980s. And then, and more importantly, the Wiener-Hopf solution derived by means of dual integral equations. In that case, I showed you how, by means of a clever use of complex analysis, it is possible first to cast the integral equations in terms of a functional equation, and second, and crucially, the functional equation can be solved by finding explicitly the spectrum of the field, that is its plane wave spectral representation. Today we will try to do the same, but for a different boundary condition. So what we will need first is to cover some material about these alternative boundary conditions, some of which may certainly be familiar to you. Let us consider, for example, the standard first order impedance boundary condition, which is well known. It is also known as the Leontonym of the Soviet scientist who introduced among the first. He was not actually the very first one, but he was the one who popularized this kind of boundary condition. Boundary condition relates the tangential component of the electric field and the tangential component of the magnetic field at the interface between an upper medium, which could be vacuum, for instance, as in this figure, and a lower half space where the medium is assumed to be characterized by a very high refractive index contrast. So if we introduce the refractive index as customarily the square root of the product mu epsilon between the two media, if the absolute value is in general complex, since the constitutive parameter of the lower medium can in general be complex, well, if this absolute value is much larger than 1, so it is a large number, this means that there is a high dielectric constant between the two media, then one can derive this kind of boundary condition in which the fundamental parameter is this eta impedance, which is nothing but the characteristic impedance of the lower medium. Okay, you may recall that this may be found by from above. One finds that to first order, at least, the transmitted wave is a TEM plane wave that propagates normally. Although this is not exact, this is a very good approximation to what happens inside the medium. And from these and the boundary conditions that relate the tangential components of the field at the interface, one can derive this impedance boundary condition, which is actually, in a proper sense, a boundary condition, meaning that one can solve an electromagnetic problem in the upper medium by enforcing this boundary condition at this interface and can neglect completely what happens in the lower medium. So this is a terminating boundary condition. Okay. There is also an alternative class of boundary conditions which are not terminating boundary conditions. They are the so-called transition conditions, and they hold at thin sheets For example, consider the simplest case, that of a resistive sheet in which we have a thin layer of some highly conducting material which is non-magnetic. So it is characterized by its dielectric, it is highly conducting, so the conduction current is much larger in absolute value than the displacement current. Sigma be its conductivity and tau be its thickness. So we have a thin sheet where the thin means that this thickness is much less than the free space wavelength, so the wavelength in the medium that surrounds the sheet. Now, we can replace, in view of this thinness, the bulk current density, that is ampere to square meters, by an equivalent sheet of surface JS. We can do that by, first of all, recalling the constitutive relation that relates the bulk current density J with the electric field. This current density will be approximately tangential, since the sheet is very thin. So it can be written as sigma times the tangential electric field inside the conducting medium. Is here we are considering the field inside the medium. Now, if the sheet is very thin, we can replace this with an equivalent surface current, which is the product of the thickness tau and the bulk current density J. So the overall dimensions of this quantity are ampere per meter. Now, if you use both equations, you will find that there is a linear link between the tangential electric field inside the medium and this equivalent surface current Js. The coefficient of proportionality is the reciprocal of the product of the conductivity and the thickness. Okay. However, since the tangential field is continuous at the boundaries, we may replace the electric field inside the medium with the electric field in vacuum at the interface with this infinitesimally thin sheet, thus obtaining a relation between the external field, the external tangential electric field, and the surface current density that flows in this sheet. So if we now introduce the electrical resistivity of the sheet, that is this parameter, the reciprocal of the product of the conductivity and the thickness, which is an impedance from a point of view of dimensions, so the unit is ohm, we can write explicitly the transition condition boxed n times the electric field, where n with the hat is a unit vector normal to the sheet, whose orientation is arbitrary since we have a double product, so it is immaterial, the choice of the direction of this unit vector. This is proportional through minus Re to the surface current density that flows in the sheet. Okay, this is a transition condition since it relates whose tangential component is continuous through the sheet, and so we have field above and below the sheet. Okay, so this is not a terminating boundary. More generally, one could consider a thin layer of some lossy, again, non-magnetic material characterized by some complex permittivity epsilon sub c, which is epsilon minus j sigma divided by omega. Okay, again, immersed in free space. Now, in this case, we can resort to the volume equivalence principle, which allows us to replace this layer by a layer of an equivalent polarization current, an electric polarization current, JE, where E stands for equivalent, which is proportional to the electric field inside the medium, so to E prime, and the coefficient of proportionality, apart from those constants, K0 and eta 0, is basically the dielectric contrast of the two media, so the ratio between the permittivities -1. Okay, so if the media were the same, the electric constant contrast would be 0, so we would have no equivalent polarization current. Okay, now again, we assume that our sheet is very thin in terms of lambda, so K0 times tau the thickness is a very small quantity. And again, we can neglect the normal component of this equivalent polarization current. So this is purely tangential. And that can be replaced by an equivalent surface current, again by multiplying JE with 6 times the thickness of the sheet. Between the tangential electric field, which is continuous across the sheet, and the surface electric current density, that functionality is again the electrical resistivity, which has this expression where you can see there is the thickness of the sheet in the denominator. The electric contrast is also present in the denominator. And this generalizes the case of a very good conductor, which can be recovered by enforcing the condition that the material is a good conductor. That is, its conductivity is much larger than omega times epsilon. In this case, you will find easily that this expression reduces to the previously derived one, that is the reciprocal of sigma times tau. Okay. Of course, it is possible to consider also the dual of this electrically thin resistive sheet. Let me admit. Okay, here we have Buongiorno Fabrizio. The dual of an electrically resistive sheet is a magnetically conductive sheet, which simulates a lossy material, a generally lossy material, which is now magnetic, so without the electric properties, with permittivity equal to the vacuum permittivity. In this case, by duality, the transition conditions relate the tangential component of the magnetic field and the equivalent magnetic surface current density that flows now in the sheet. So the sheet now supports a magnetic surface current density rather than an electric surface current density. And the proportionality between the tangential magnetic field and the current density is this coefficient R sub m, where m stands for magnetic, which has the dimension of an admittance, so we measure it in Siemens, and which is the dual of the previous one. It is inversely proportional to the thickness of the sheet and to the magnetic contrast of the two media. That is the ratio between the permeability minus 1. So that again, if the medium were non-magnetic, this contrast would be equal to 0, and we would have an infinite admittance, okay, which means a 0 impedance. So basically, the sheet is not there. Note that in this case, since we have a surface magnetic current density, the tangential electric field is now discontinuous, and the jump of the tangential electric field is related to the magnetic surface current density, whereas the tangential magnetic field is in this case continuous across the sheet. So it's the perfect electromagnetic dual of the previous situation. It is also possible to combine the two cases, that is the resistive sheet on one hand, which supports an electrically conductive sheet, which is conveniently by writing the respective transition conditions, as you can see in these two boxes. On the left, you can see the case of resistive sheet, in which we have written the electric field, which is continuous, whose tangential component is continuous, as half the sum of its values on the upper and lower sides of the sheet, and the 2 that was in the denominator of this average has been taken to the right-hand side. Whereas on the right-hand side, instead of the surface current density, we can see the jump of the magnetic field. And in this case, the tangential electric field is instead continuous. Dually, for a magnetically conductive sheet, we have continuity of the tangential magnetic field, and we can write the boundary condition, as you can see here, where again, we have written everything in terms of the values of the fields on the plus or minus sides of the sheet. Now, in this form, it is easy to combine the two conditions. So by simple addition and subtraction, we get the transition condition that holds for this combined case with m, depending on the choice of the double signs. So you can see that n vector E, either on the plus or minus side of this combination sheet, is related to the plus magnetic field through these coefficients that mix together the electric resistivity. Okay. It is interesting to note that in general, these are also transition conditions. That is, generally, both the plus and minus fields are different from zero. However, there is a particular choice of the resistivity and conductivity that make this transition condition actually a boundary condition. This is because if you let, for example, Re be equal to 1 divided, what happens is that, for example, for the upper choice of the signs, this term in this bracket vanishes. So if you now consider the upper choice of the signs, you have a relation between the upper electric field and the upper magnetic field only. So this means you have a boundary condition that is a terminating boundary condition for the upper half space. Conversely, if you consider the lower choices of sign, in this case, it is the first bracket relation between the lower electric field and the lower magnetic field. So that, again, you have a terminating boundary condition, but in this case, for the lower half space. This means that what you have obtained is actually a boundary condition that is the standard impedance boundary condition that in this case becomes opaque. So it is not penetrable by electromagnetic radiation. And this is the form of this boundary condition where the equivalent surface impedance is given by twice Re or the reciprocal of twice Rm. Okay. So if you are able to solve the problem for a half plane in a case of a resistive sheet and of a conductive sheet, then by combining them, you may also find the solution for an impedance sheet. Okay, so what we will do now is to consider the Sommerfeld half plane problem by considering a resistive sheet. Let me drink.
You are muted.
Professor, excuse me, could you please turn on the microphone?
Ah, okay. I don't know why, but the microphone was turned off. Can you hear me now?
Yeah, now it's okay.
Okay.
Now we can hear.
For how long was this happening? Just to know.
1 minute.
Okay. So I will repeat you.
So you just the title slide, that's when it stopped. The Sommerfeld problem.
Okay. So I was just commenting this configuration, but it is almost self-explicative. This is exactly the same configuration that we considered. The previous conditions on the resistive half plane are different, and those boundary conditions relate the electric field, which has only a z component, and the jump of the tangential magnetic field, that is in this case the jump of the x component of the magnetic field of the half plane. Note that field is continuous across the half plane because so no jump of tangential electric field. Okay, we will solve this problem by using the same approach as in the case of a perfect conductor. And so we will introduce from the beginning the angular spectrum representation of the fields. This means that the electric field is represented in terms of this kind of integral in which P sub E is the spectrum as a function of the cosine of alpha, which is the spectral angle. And correspondingly, you have the representation for the magnetic field, in which you see inside the integral there is also an additional sine of alpha factor. Or equivalently, if you let lambda be equal to the cosine of alpha, you solve this lambda integration variable, which is actually a normalized version of the kx wave number. So you can recognize the exponentials of the plane wave that make the spectrum. Okay. This latter representation is actually the most convenient, in particular by enforcing the boundary condition on the resistive sheet and using this latter representation. What we find is this kind of integral equation in the upper box, where you can see now the integral equation is very similar to the one we derived. However, now we have an additional term inside these brackets here, which is a constant actually. It is the ratio between 2 times RE divided by the characteristic impedance of free space. Okay. Our unknown is the spectrum, and on the right shell there is actually the incident field. Lambda 0 is again a shorthand notation for the cosine of the incident angle phi 0. On the other hand, if you enforce that is 0, or better hx is 0 on the aperture for negative values of x, which is equivalent to enforcing the fact that there the current density simply is 0 because there is no material there. Okay, in that case, you will find another integral equation, which is simpler, which is this one, and that's an homogeneous integral equation that holds for negative values of x. So we have our pair of integral equations that hold on complementary parts of the plane y equals 0, and therefore they are dual integral equations. They also have a different kernel. And the way we will solve them is exactly the same for the perfectly conducting case. So as in the case of a perfect conductor, we derive immediately that the spectrum is an upper function, that is a function that is analytic in the upper half plane of the complex lambda plane. Whereas the first equation will be satisfied and the residue theorem, provided that the function u can be cast in this form, better the function u multiplied by this bracket can be cast in this form, where you can see there is a pole singularity when lambda is equal to minus lambda 0, and that comes from this term here. Then there is this normalizing factor, which is such that the residue of this term here is equal to 1. And L1 is an arbitrary lower function. That is a function that is analytic in the lower half plane. We also have this additional lower function, L2, which gives no contribution to integration along any closed contour in the lower half plane. And now the problem is recast in terms of a functional equation. So now we have no integrals, but we have a relation, a functional relation between 3 unknown functions. That is the upper function on the left-hand side and 2 lower functions on the right-hand side. Since those functions, however, are not equal, we can proceed as we did in the previous lesson and consider that the equation can be solved provided we are able to split all the upper functions on one side of the equality and all the lower functions on the other side. So what we need to do is to split this function here in in brackets, or better, its reciprocal, as the product of two terms, the so-called upper-lower split functions, k sub plus or sub minus, which are parameterized by this eta over bar, which is the constant that resistivity of the sheet and the free space characteristic impedance, and which are linked one another, since k plus evaluated in minus lambda is equal to k minus evaluated at lambda. So we just need to find one of them. Now, the general way to factorize a given analytic function into the product of two upper-lower split functions, which I remind you are two functions that are analytic and without zeros, respectively, in the upper or lower half planes, is something that in general could be even impossible, or we wish to express those functions in analytical terms. We will not enter into the details of the existing techniques to perform this splitting. However, be aware that it is always possible to do that numerically. So it is possible to find integral expressions for those two split functions that, even if cannot be evaluated in terms of any known functions, can anyway be evaluated numerically, so to an arbitrary precision or accuracy as you need. In this specific case, however, it was indeed possible to find an explicit representation for the split functions. That was done for the first time by Senior in 1952. That was a quite complicated expression that was later cast into a somewhat simpler form once the so-called Malyuzhinets functions were introduced by Malyuzhinets in 1958. And this is the quite complicated looking expression for the upper split function, for example, as a function of the normalized eta and cosine of alpha, where you can see there are a bunch of terms. The simplest is this sine term here. Then we have these curly brackets squared, which contain the Malyuzhinets function psi sub pi, which is evaluated with two different arguments here and there. The denominator is just a constant, since it is the function psi evaluated at pi over 2. And finally, we have these curly brackets, which are reciprocated. You can see -1 in the exponent, where, again, we find trigonometric functions, the arguments of which contain both alpha, the spectral angle, and this angle theta, which is defined by this relation. Its sign is the reciprocal of the normalized impedance of the sheet. What is the Malyuzhinets function psi sub pi? This is more precisely the Malyuzhinets half-plane function. That is because Malyuzhinets actually introduced a whole class of functions, which are analytic functions with singularities in a complex plane, and introduced them in order to solve the general problem of plane wave scattering from a wedge with some internal angle, which is arbitrary, on whose faces impedance boundary conditions hold. So we have a Malyuzhinets function for any internal angle of the sheet of the wedge. In particular, this kind of function psi sub pi is the one that occurs in the treatment of the half plane, that is the Sommerfeld problem we are considering. And this is one possible explicit expression for this function that is given in terms of an exponential of an eta, is the upper integration limit. And here you have thing as a function of u, the integration variable. Okay. However, there is a huge literature on this function. There are approximate expressions, asymptotic expressions. There is everything you may wish about this function. Alpha in general is a complex argument, and we may note that at least if the resistivity of the sheet goes to infinity, so basically the sheet disappears, the upper split function tends to 0, as it must, and the way it becomes 0 is made explicit here. So it goes to 0 as the inverse of the square root of the normalized impedance eta. The other interesting limit is when instead the conductivity of the sheet becomes very large, something limit, eta goes to 0. And one can easily see that it is the square root of 1 minus lambda tick up to find in the previous lesson. This can also be written equal by means of a trigonometric sine of alpha divided by 2. Okay. Now, coming back to our functional equation, if we introduce the split form of on the left-hand side, and we then take the lower split function on the right-hand side of the equation, what we get is this form here, which is which now contains only upper functions on the left-hand side, and on the right-hand side, we can see a bunch of lower functions, L1, K minus, L2, is a pole, and since the pole is a pole that makes the entire in the lower half plane, so pole on the left-hand side, and we do that by subtracting from both sides of this equation a term which is a constant divided by lambda plus lambda 0. So the constant is, of course, chosen in such a way that what remains on the right-hand side does not contain the pole anymore. Okay, and this is the right constant to be used. It's the upper function evaluated at lambda 0. So once you have done this, you have achieved the form in which the left-hand side is entirely an upper function, so it's analytic, the upper half plane, and the right-hand side is now entirely a lower function. It is analytic in the lower half plane, but since those are equal, since the left-hand side is equal to the right-hand side, we may conclude that both the left and right-hand sides, so they are entire functions. And so we are in the position of using Liouville theorem. We will do that once we know the behavior of the functions, or better, of the left or right-hand sides at infinity in the lambda plane. That can be determined by an asymptotic analysis of the functions involved. In particular, the Maljuginets function has this behavior at infinity, which in turn implies that the upper split function is a constant when lambda tends to infinity, and of the upper function u, which is proportional to the spectrum. And as you may recall, this is also proportional, therefore, to the spectral current density that flows on our half plane. Well, that can be obtained by means of the edge condition, since the current density translates directly via Watson's lemma into the behavior at infinity of its Fourier transform. So in this case, what we obtain is that at infinity, the upper function becomes the inverse of lambda. So therefore, if you now consider the entire left-hand side of this multifunctional equation, you will discover that this left-hand side goes to 0 at infinity. So it is an entire function that is infinitesimal at infinity. So this means that Liouville theorem tells us that this is a constant, and this constant is equal to 0. Since it is a bounded entire theorem, and since it is infinitesimal at infinity, the constant must be equal to 0. So we can directly equate to 0 the left-hand side, as we did in the perfectly conducting case. If you do that, extract that becomes proportional to k plus evaluated at lambda plus k times k plus evaluated at lambda 0, this is a constant, divided by lambda plus lambda 0. Or in terms of alpha, the spectral angle, you have the expression here below in the box. So the problem is in principle solved. So we know the spectrum of the electric field when the boundary condition is that of a resistive sheet. Something very similar can be done dually if you have instead a conductive half plane. Everything else is the same, so we again have a TM polarized incident plane wave. The difference is that now the electric field will be discontinuous across this sheet because now there is a magnetic current density that flows there instead of an electric current density, whereas the magnetic field, or better, the tangential magnetic field, will be continuous. So as you can see in the plane wave spectrum representation, we have now a double sign in the electric field. That is, whereas we don't have that in the magnetic field. Now the spectrum PM, where M stands of course for magnetic, is proportional to the spectral magnetic current density that is supported by this conductive half plane. So apart from minor modifications, the procedure is exactly the same. You enforce the boundary conditions, that is, you have a relation between the magnetic field and the jump of the electric field through the magnetic conductivity, Rm, and the magnetic field is continuous across the sheet. You have, in the same way, a pair of dual integral equations that are quite similar to the previous ones. In particular, as you can see, the left-hand side of this equation is almost the same, only the expression of this constant is different. Whereas in the right-hand side, in addition to this exponential function, we have this constant here, the square root of 1 minus lambda 0 squared. And in the second integral equation, instead of having only the spectrum, we have the spectrum divided by the square root of 1 minus lambda squared. So we start from this latter integral equation to find that this ratio must be an upper function. We will call it u. And we again proceed by splitting what is on the inside the integral of the other integral equation. If you do that, you will find this kind of functional integral equation where, however, the split functions are exactly the same as those used in the resistive case. The only difference is that now the parameter is eta m over bar, which has a different expression. It is inversely proportional to the magnetic conductivity. But whatever, any other thing in this equation is more or less the same, apart from the square root, which is a constant, which is in the numerator of this ratio. So the procedure is again the same. You will find by means of Liouville theorem that the upper function has this explicit expression, or in terms of the spectrum given in terms of the angular variable alpha, for the magnetic spectrum in this case. So we are able to solve the problem analytical conductor case. And as I mentioned at the beginning of this lesson, by combining the resistive sheet and the magnetically conductive sheet, you are able in general to find a combined sheet for particular cases of the parameter can be reduced to an impedance sheet. So if you are interested in treating a half plane where impedance boundary conditions of the Leontovich type hold on the two faces, then you can do that by a simple combination of the solution I have illustrated you so far. Just for your information, if you were interested in the case of a half plane where two different impedance boundary conditions hold on the upper and lower faces of the sheet, well, in that case, the Wiener-Hopf method is not much helpful. You have to resort to the full theory of Maljuginets for the treatment of an arbitrary wedge with impedance boundary conditions on its faces, which is something that is not entirely different theory that maybe in a future edition of this course I will find the force to introduce. Okay, having said that, we'll deal with the analysis of the diffracted field. However, it's time to make a break. So let's start again at 11. Okay. So see you later. see. Okay, here we are back. What I will show you now is something about the evaluation of the diffracted field. We have now solved, in principle, the Sommerfeld problem. That is, we know the plane wave spectrum of the field. However, the integrals that express this field cannot generally be evaluated in a closed form. So an asymptotic analysis is necessary. Well, actually, in the case of a perfect conductor, the integral can be evaluated in a closed form, and this is one of the things that we will show first. However, in the general case, we will need to perform an approximate analysis, which is asymptotic in nature. Let us start with the perfect conducting case. There is a particular case of a resistive half plane in which the resistivity is equal to 0. The starting point is, again, the angular spectrum representation of the scattered field, which is repeated here. You can see there is an integral, which is performed along a specific contour in the complex alpha plane. This constant here is the amplitude factor of the incident field, and it is taken outside for convenience. By linearity, the scattered field will be also proportional to the amplitude of the incident field. And we have a double sign corresponding to the two half spaces above and below the sheet. Now, in the previous lesson, we were able, by means of the Wiener-Hopf technique, to find an explicit expression for the spectrum P sub minus cosine alpha divided by cosine alpha plus cosine phi 0. Now it is convenient, and it is done in most of the treatments, to rewrite this by using some trigonometric identities. In particular, you can write the square root functions above in terms of the sign of the half angles, alpha divided by 2 and phi 0 divided by 2. Whereas in the denominator, you can represent the sum of the two cosines as a product, and conversely, the product of the two sines in the numerator can be represented as a sum. And if you do that, you will find that the spectrum can be equivalently be expressed, as in the bottom of this slide, as proportional to the difference between two secant functions. The secant is the reciprocal of the cosine function, okay? The arguments of those secant functions are alpha plus phi 0 divided by 2, or alpha minus phi 0 divided by 2. So for the spectrum, this expression in the box, okay? Now, we will and to this aim, we need to know the singularities of the integrand. And since we have secant functions, secant is by itself the inverse of a cosine, so we need to avoid those points where the cosine is equal to 0, and this happens when its argument is pi over 2. So it's easy to see that we have poles at those locations, alpha p1 and alpha p2, which are respectively given by pi minus phi 0 or pi minus. Now, as we will see in a moment, those poles are very important because they offer, through their residue contribution, the possibility of recovering on one side the reflected wave in terms of geometrical optics, and that comes from pole number 1, whereas the other pole, number 2, gives us the possibility of offsetting the incident wave, that is canceling the incident wave, in the region where, from a geometrical optics point of view, we would have complete shadow. And in fact, the procedure that we will follow to evaluate this integral is the usual one. We will consider a deformation of the integration path that is originally the black one, that detours around poles, and is indicated here, to the new path, which is actually a steepest descent path that goes through the saddle point located on the real axis at phi. Phi is, of course, the observation, so we have dependent saddle point. This phi can go all the way from 0 to pi, okay? And this is the location of the two poles, which are symmetrically located with respect to pi. Okay. Now, this steepest descent path in general is used to perform an asymptotic. We'll be able to actually evaluate exactly in analytical terms its contribution. That is because we are in the case of a perfect conductor. Now let us examine the location of the poles that again are at pi plus or minus phi 0. Now geometrically, those angular locations define the so-called shadow and reflection boundaries, SB and RB. In particular, pi minus phi 0 is the reflection boundary, whereas pi plus phi 0 is the shadow boundary. They are indicated here and in the following slides with different colors. And the meaning is quite simple. Of course, the shadow boundary is the boundary that separates the illuminated portion of space, where in geometrical optics you have incident rays coming from some angle phi 0, from the region below, beyond, better, the half plane on which rays are not able to penetrate. Okay, so that's a region of geometrical shadow. On the other hand, there are also reflected rays impinge on the half plane, and so therefore the reflection boundary takes this form that originates from the edge of the half plane. Okay, so we can divide the entire three-dimensional space into three distinct regions. In the first one, that is represented here in a shadow, we have both the incident rays and the reflected rays. In the second region, in this wedge here, we have only the incident rays because we are beyond the reflection boundary, but still we have not reached the shadow boundary. And finally, in the third region, we are in the geometrical shadow, so we have neither incident nor reflected rays. Now, this classification of regions actually corresponds strictly to the relative positions that the steepest descent path may have with respect between 0 and pi minus phi 0, so that the saddle point here at phi in red, this point here, is located on the left of the leftmost pole here at pi minus phi 0. Then what happens is that if you deform the integration contour from the black one to the orange one, you will need to cross the shaded areas here, and in particular, you will find the residue contribution that comes from this pole here. So by means of this deformation, initial the incident field plus the scattered field, by manipulating the scattered field by means of this change of integration path, we can express the scattered field as the sum of the contribution coming from the steepest descent path, and that is by definition the diffracted wave, okay, plus the residue contribution of the pole that is located at pi minus phi 0. And if you evaluate it, you will discover that it is exactly the reflected wave. So this pole is a responsible term here, which is a simple plane wave weighted by a unit step function. The unit step is equal to 1 in this shaded area here, the top left, but it is equal to 0 outside. Okay, so we get, by means of this discontinuous unit step function, if we now increase the observation angle phi beyond pi minus phi 0, we get a situation like that, in which, as you can see, the portion of the lambda plane that is swept when changing the integration contour does not contain it. So basically, the scattered field is entirely of the steep. That is, it is a purely fractal wave in this direction and shadow boundaries. So that, again, the total field will be given by the sum of the incident field there plus a diffracted wave. That is the if phi is even larger than pi plus phi 0, so that now phi here, the saddle point, is on the right of both poles, what we find is that we have a residue contribution, but now this comes from the green pole here at pi plus phi 0. So in this case, the scattered field is the sum of the contribution of the steepest descent path, that is the diffracted wave in red, plus this discontinuous contribution, which is, after doing the algebra, nothing but the opposite of the incident wave. However, because of the presence of this unit step function, this contribution only occurs beyond the shadow boundary. So this means that beyond the shadow boundary, we have this green term that offsets, that is, it cancels exactly the incident field. Okay, so that the total field in this shadow region is made up of the diffracted field only. So what penetrates in the shadow region is just the diffracted field, and the terminology is, of course, modeled on Sommerfeld definition. If there is some by definition that must be. Okay, having said that, we are able to perform our asymptotic evaluation, that is, employ the saddle point technique without any special consideration of the poles. And if we do that, we discovered that the scattered field can be approximated asymptotically by means of this field here, where in the superscript we have D, that stands for diffraction, and NU, that stands for non-uniform. The method gives you, I suggest you to perform the calculations, this expression here of contains the dependence on rho, which is explicit plus a modulating term to the angle. Okay, so this is a diffraction pattern. We could use this terminology. And this is typically cast in the form of the second line here, where you can see there is the amplitude of the incident field, then there is the cylindrical wave, and everything else, this red factor here that depends on the angle phi, and which is parameterized by the incident angle phi 0, whose explicit expression is given below, and that is by definition a diffraction coefficient. Okay, so in this case, it's non-uniform comes from the fact that we have evaluation with any pole singularity. Okay, the expression is of course proportional to the integrand, that is the difference between the two at the saddle point. The observation point, and also there is a nice symmetry between phi and phi 0. So if you switch them, nothing changes, and that is of course an inheritance of reciprocity. So if you switch the role of the observer and of the source, the situation is unchanged, as it must. Now, the problem with this non-uniform evaluation is that first, these the reflection boundaries and shadow boundary appearance of residue contributions that come from the optical. So this is not field, which is instead, for physical reasons, continuous everywhere outside the half plane. But even worse, for any rod, the accuracy of this asymptotic expansion decreases and can decrease even dramatically if you are very close to those reflection and shadow boundaries. That is because when you are close to those locations, those angular locations, what happens is that your saddle point may become very close to the pole. Now, if you remind the principle by which we derived the asymptotic expansion through the saddle point technique, what we did is take the starting point, the saddle point, and having the distance by singularity. Now, if this distance becomes a very small or even a vanishingly small quantity, this convergence radius, this means that even though in principle the asymptotics is exact, that is when rho is very large, this non-uniform asymptotics is correct. However, the point is that you could be forced to have a really very, very large value of rho if you wish to find some accuracy in your representation, which could be you will also deal with finite values of rho. So explicitly, there is a pole, or that there may be a pole close to your saddle point, and that is the idea behind the uniform asymptotic evaluation of diffraction integrals. Now, these problems in the perfectly conducting case can be solved at the fact that in this specific case, there is an explicit representation of this standard integral, that is the integral along the steepest descent path, alpha minus alpha 0 divided by 2 times the exponential, can be expressed in a closed form in terms of a modified form of the Frenet in one of the first lessons. Form is the so-called Clem-out transition function, defined here below. Multiplied by a modified Gaussian exponential. Okay, with continuity in this. There is not a discontinuity, sorry. It is a double choice, which is we have two possible alternative representations. Okay, thanks to this expression, we can now write the entire field by summing the incident and scattered field as in this expression, where you can see the difference between the two second functions inside the integral has now become the difference between two functions with diffraction. So the discontinuous residue contributions that contain the unit step functions, okay, the one associated with the reflected wave first, and the one associated with A. Now, in spite of the functions, actually, it turns out that this expression is continuous everywhere, even across the shadow or reflection boundaries. The position function, that is a sort of symmetry property, that relates the value of the function at z at minus z, their sum is equal to this proportional to this modified Gaussian integral. And so if you employ this property as in this box, where now the expression, so we have removed any unit step function. Okay. So basically, the uniform evaluation has removed the discontinuities. However, it has complicated the dependence on the radial variable, which is not that of a simple cylindrical function anymore, but it's mediated by this kind of transition function. An alternative way of expressing the same total field makes use of a different transition function. In particular, Robert Kuyum-Jan and Patak in their paper, the historical paper of 1974, in which they introduced the uniform theory of diffraction, they cast the diffraction coefficient, the uniform diffraction coefficient in this case, in the form that is reported here, where they used a transition function fkp, which is related to the Clem-out transition function as in the bottom of this slide. And again, this expression is continuous everywhere. Note that the UTD transition function behaves as you would expect from a transition function. That is, if the argument is x, say a real number, when the argument is a large number, then the magnitude of the transition function tends to 1 on the left verticals to 0. So basically, the function resides a small quantity, the magnitude tends to 0. Okay, so we have a smooth transition from 0 to 1. So let's say that the black and white world of geometrical optics becomes a whole grayscale mediated by the UTD transition function. Okay, and therefore the difference between those two second functions weighted by the Coulomb-Janin path-arc transition functions has the same form as the simple abrupt difference of second functions that occurs in the perfectly conducting case. So if instead of the transition function you have now the unit constants, you will be able to recover the formula that we derived for the perfectly conducting case evaluation. Everything can be expressed, for example, as the sum of the field that is present everywhere but in the shadow region. So that's the reflected, the incident geometrical field, plus the reflected geometrical field, okay, in the appropriate region, so before the reflection boundary. And finally, we have the diffracted wave contribution that is present everywhere. The diffracted field, in particular, can be written in terms of the transition function of Coulomb-Janin path-arc. Previously, we expressed the total field, whereas now in this slide, you have the representation of the diffracted field only in terms of a uniform diffraction coefficient. So note that the diffraction coefficient can be used either for the diffracted field or for the total field. That depends on the context. And of course, the expression is different. So basically, this expression allows you to find a continuous representation everywhere. That is because now the expression is discontinuous, because now the diffracted field is discontinuous, and the Coulomb evaluated with these output values in the arguments, and this makes the entire expression discontinuous at the reflection and shadow boundaries. However, the discontinuity of the diffracted field is equal and opposite to the, so all in all, there is a perfect compensation. Okay. Now, having said that, for the perfectly conducting case, we are able to treat the resistive half plane, where the procedure is in principle the same. However, the integrand is more complicated. And here I have reported the scattered field for a resistive half plane, where in black you have the parts that are common with the perfectly conducting case, whereas this blue part is novel, where it were two in the perfectly conducting case actually. And that contains the split functions involving the Malhusian functions that I showed you before. Now, because of the presence of this blue pair here, we cannot evaluate exactly the integral on the steepest descent case. We don't have only the second functions and whatever else, so able to close the integrals analytically. So we have to proceed the way. We'll follow is to deal with pole singularities. In the theory of diffraction, we will show the so-called additive approach that was introduced by van der Waerden in the 50s. There is also an alternative multiplicative approach that was followed first by Pauli and then by Clément, but it is somewhat more complicated in this case, so it is more convenient to use the additive approach. It has been shown in these two approaches are actually asymptotically the same, even though they will not give you the same answer to the dominant asymptotic order. However, if you include all the asymptotic orders, the two approaches are the same, so there is no actual difference. And now, the additive approach consists in extracting out the poles and then resumming back. Now, recall that the the upper split function has this complicated expression here in terms of the Maleusinate functions, psi sub pi. But in particular, I have rewritten it here in order to make it clear that we have an additional term here in the denominator, this blue term, that is the cause of the appearance of third pole singularity that are present also in this case, and they come from the second functions, also part of the integral, which corresponds physically to the occurrence, to the excitation of a surface wave. That is a surface wave that is supported by our resistive sheet. Since the pole is actually equal to minus theta, and this is the inverse sign of the reciprocal of 1 divided by the normalized impedance, and one can show that the surface wave that would be supported by this resistive sheet has a wave number that is related to this quantity here. Okay, so we have to deal with 3 instead of 2 singularities. However, the procedure is the same for the 3 poles. So as I was mentioning, what we do is that we first subtract from the integrand, as q of alpha, something that contains the pole singularities with the right constants, u tilde, so that the difference now is without any pole singularity. So basically we are regularizing the integral by subtracting the term here in the summation where I goes from 1 to 3 because there are 3 poles. But of course we have to sum back what we have subtracted. However, when we sum this back, we are able to integrate only the seconds, as you can see from the form of these others. Now, since we have only second functions, we can close analytically these integrals in terms of the Clemaut or Kuyum-Jan and Patak transition functions. What remains inside the integral in brackets is now a regular function, and therefore we can proceed in the asymptotic uniform approach. So the basic first order saddle point technique. If you do that, this is the explicit expression of q of alpha, by the way, but that's important. If you do that, so if you perform the standard non-uniform asymptotic evaluation of the diffracted field coming from the first integral in the previous expression, you will find that the non-uniform diffracted field takes this expression in which you have a non-uniform diffraction coefficient in red, which is a version. However, this is weighted by something more, which contains the split functions that occur in the resistive sheet case. In addition to that, of course, you have to include also the contribution that have been extracted out, and they contain the transition function, for example, the Kuyum-Jan-Patak transition function. If you include also those contributions by summing algebraically together the two things, you obtain the final uniform diffraction coefficient that is in the case of a of the total field everywhere, and that comes from the fact that the discontinuity in the exactly compensates the correspondence of the reflection and shadow bound. What I've said in this lesson, as in the previous one, is taken from this beautiful book by Senior and Volakis, Approximate Boundary Conditions in Electric, where the title is quite misleading because the title actually corresponds to perhaps only the first 2 chapters of the book, because the rest of the book is the application of those boundary conditions to scattering problems. And in particular, chapter 3 deals with the Wiener-Hopf method that I have tried to explain you. The next chapter deals with Maleusinet's theory, and then there are other beautiful chapters after that. Then our attention today, and as I anticipated you in our previous lesson, we have now a concluding special effect. There is my colleague who was first a brilliant PhD student here, and then he worked with us for many years and is now a brilliant scientist at the CNR, Consiglio Nazionale delle Ricerche in Rome. We'll talk you about localized waves that are quite interesting wave objects, and that's the traditional way in which this course concludes. I thank him very much for his availability, and I leave you the field. Maybe we can have just 5 minutes to recover our forces, and then in 5 minutes, Walter will start with the seminar.
Okay, I hope you can hear me. Okay, can somebody confirm that you can hear my voice?
We can hear you.
Yes, we can.
Okay, thank you. Okay, let's start this presentation. Okay, I thank Professor Paolo Burghignoli for giving me some room to talk about localized waves in this course. It's great. And I will give this talk of about 45 minutes, let's say, and I will not give too many details about the analytical treatment of these objects that you will find in the slide, but I will try to give you an idea what are the potentialities of these objects in many electromagnetic, let's say. So I will start with a brief introduction about diffraction and non-diffracting waves are basically the main property of localized waves. Then I will
Hello?
talk a little bit
I'm
about
sorry to interrupt you.
compact complex spectral objects. That means the connection that exists between rays and plane waves that is helpful to understand how radiation occurs from planar aperture in order to create focus beams and focus pulses that are the constituents of localized waves. This will give me the opportunity to talk about compact spatial temporal wave packets, as I said, localized beams and localized pulses, and representatives of these objects are Bessel beam waves. And finally, I will draw the conclusion. So, as you know, diffraction is always present in any kind of wave phenomena. And in this seminar, we will try to answer some fundamental questions about diffraction that are basically if it is really possible to beat the diffraction limit, to push over the non-diffractive limit of waves, if it is possible to focus electromagnetic energy over an arbitrarily small region, and if we can do that in any frequency range, in particular at millimeter waves or microwave frequencies. Well, in order to give an answer to the problem if it is really possible to avoid the spatial spreading of waves caused by diffraction, we can data probabilities when Stratton actually predicted the existence of an entire class of solutions that do not undergo diffractive spreading as they propagate. These solutions, Helmholtz equation, are basically known as Bessel beams, but later, I would say in the 80s, they belong to a wider class of solutions that, in theory, have diffracting features. This wide class of solutions are namely known as localized waves, and sometimes it is useful to distinguish between two other classes of solutions. Those that are monochromatic solutions that exist for a single frequency, that are Bessel beams, and polychromatic solutions, though I would say solutions that possess a given frequency bandwidth, and these solutions are X waves. Well, now I would prefer to give an introduction about this terminology about compact spectral objects before introducing the properties of localized waves. And in order to give an explanation of how rays can be connected to plane waves, it is useful to first talk about spectral representation. So in order to have a clear picture to understand radiation from an aperture distribution, it is good to relate the spatial spectral and the plane wave spectral representation. Here you can find this representation in representation of the field radiated by a linear array of line sources given as a superposition along the spatial coordinate y of the green functions of this line source distribution along the x-axis. And in red, you have the same representation of a different and alternative representation of the same field with a spectral representation with this sort of Fourier integral in terms of the spectral variable eta, that is number to the one. Well, the link between these two interpretations is provided by exploring the plane space spectral expansion of free space green function that is given by this relation here that relates the Hankel function of 0 to vertical species to this integral in terms of the spectral variable eta. If you use this representation of the Hankel function here, you can go back from one interpretation to the other. Now, it is interesting to assume a source distribution that is of the following type: an amplitude distribution and a phase distribution that are slowly varying function with respect to the wavelength. And it is useful to have an asymptotic evaluation of these two representation with respect to such an aperture distribution, because the asymptotic representation of these integrals lead to a very interesting geometrical interpretation. Indeed, if we exploit an asymptotic evaluation of these two integrals, and we can do that by exploiting the large argument asymptotic expansion of the Hankel function and by evaluating saddle points of this integral, as has been shown in this course, the evaluation of the saddle points of this integral equation gives you a straightforward geometrical interpretation. Indeed, if we evaluate the derivative of the phase term of this integral with respect to the spatial, we obtain this relation here that is just telling us that the main contribution of this integral to the field that is observed at an arbitrary location yz is given by rays that connect with straight lines the part of the source that is contributing to this point selected by the observer. In other terms, is the observer that selects the portion of the source that contributes to radiation. But it is true only when the source can go from A to B, from any point to A to B. But for endpoints that are fixed at the A limit on the left and the B limit on the right, we have that the observer can no longer select the source. And this means that the whole spectrum have this endpoint contribution that excites the whole part of the spectrum. The same interpretation can be obtained if we use the other spectral representation of the field, and basically you get the same result, even if expressed in a term by, again, evaluating the saddle points of this integral here. And these results again links the spectrum to the same geometrical interpretation. And this conclusion closes the loop that basically ray trajectories in the spatial domain are associated to plane waves in the spectral domain, because here we have that this angle is associated to the spatial angle of the spatial interpretation, while here this angle theta is associated to the spectral angle of the plane wave that is propagating along a given direction. Now we can go a step further and assume that the phase term that we used in the aperture field distribution is no longer real but can be complex. And this brings you to a different evaluation of the a different asymptotic evaluation of the integral by means of the steepest descent technique and that you have seen in this course. And if you assume this generally complex phase distribution, the result is that basically you have that the imaginary part that you have added to this phase contribution acts as an exponential taper to the amplitude distribution of this source. And this is actually practically a famous example of a Gaussian beam that is actually a beam that has an exponential taper on the source and is characterized by an imaginary part of the phase that is equal to the square of the spatial variable along the y-axis divided by a terms 2b that is in connection with the dimension of the source. And provided that you use this expression for the imaginary part of the phase spectrum, you have some nice formula that tells you how the diffractive spreading of the beam as it propagates is related to the aperture of the source. And basically you have that as you propagate at a distance that is called the Rayleigh distance ZR, you have that the beam width of this Gaussian beam is spread about a factor that is proportional to the square root of 2. Such a complex gives rise to saddle points now that cannot be captured if we perform the integration on the real axis. And so we have to analytically extend the real spatial axis to the complex plane. And this can be done by evaluating the steepest descent path over the complex plane, as you have seen in the previous slides of this course. And this opens to a very nice interpretation of this phenomenon of generation of a Gaussian beam from a finite aperture that tells you that basically you can still have a compact spectral representation of this phenomenon if you use a complex source. You can imagine that this Gaussian beam that is generated over a real space that is constituted by the z-axis and the real y-axis is generated by a source that is generated over the imaginary axis and gives contribution to the real field generated on the real aperture through complex radial trajectories. And the same conclusion can be obtained even if we start from the spectral representation. So basically, this last example is basically the analytic continuation of what we have seen in the previous slide in the real case. One interesting application of these methods and of this spatial spectral representation with complex source points is given by a particular wave packet that is known as focus wave modes. Indeed, if we imagine to have a complex source point that is located along the imaginary z-axis, and we have that this complex source point travels over a line parallel to the real z-axis at the speed c, that is the speed of light, we have that this solution no longer generate only a Gaussian beam, but a mode that is focused, that is spatially confined over both the real y-axis and the real z-axis, and propagates without changing its shape. Basically, we have obtained with this particular source that is traveling over a line that is parallel to the real z-axis but is located over the imaginary z-axis, a pulse that does not suffer neither diffraction nor dispersive spreading because it travels along the real z-axis while maintaining its shape that is narrow along both the y and the z-axis. And as we will see, this particular property of pulses that are confined along both the transverse and the longitudinal direction and travel while maintaining unaffected their shape while they propagate is shared by most of the wave solutions that belong to the class of localized waves. Well, in order to introduce localized waves, it is useful to start from the homogeneous wave equation in time domain. And then to switch this, to put this homogeneous wave equation in a cylindrical reference frame. When we do that, we can apply the Fourier method to obtain a generation of a solution to this differential equation in terms of Fourier or Bessel integrals. In particular, we have an ordinary Fourier transform with the spectral variable to the frequency and to the spectral variable to the wave number spectral variable key z, and also with respect to the spectral variable rho in terms of Heckel transform because of the cylindrical coordinate transformation. And hence, indeed, here the kernel is a Bessel function of nth order. When we assume, however, an axially symmetric solution, this problem simplifies a little bit. We no longer have the dependence from the azimuthal coordinate, and the integral is given in terms of an ordinary over a Bessel function zeroth order instead of nth order. And we can still simplify this integral representation of a generic solution of a wave in the reference frame if we exploit the separation relation and we enforce the vertical wave number, the wave number along the z-axis to be real, basically by enforcing the Kiro to be in the radiating regime. And if we do that, this integral representation collapses in this one where we have only two integrals, one with respect to the angular frequency omega, and the other one with respect to the radial wave number that is now allowed to go only from the minus keynote and plus keynote, that is the visible range, because of the hypothesis stated here. And this representation is given in terms of an arbitrary spectrum that depends on both the radial wave number and the angular frequency. So far, this expression is not referring to any localized wave, it's just a solution to the wave equation in a general solution. The wave equation is integral reference frame while assuming only wave numbers that belongs to the visible range. What we need to have a particular solution of a wave in a cylindrical reference frame? Well, we have to give an expression to this arbitrary spectrum as a function of Kiro and omega. And if we want a Gaussian beam that is a monochromatic solution, since it is monochromatic, we will have a Dirac function in terms of the angular frequency variable that fixes the frequencies to be only omega 0, omega naught, a single frequency that we set. And then we have the Gaussian distribution with respect to the key rho variable here. And if we enforce this expression in this integral up here, we obtain the Gaussian beam that can be seen under the paraxial approximation is given in the closed form reported here. On the other hand, we can also have a polychromatic solution if we allow the dependence from the angular frequency no longer given by a Dirac function, but again by a Gaussian distribution. And if we enforce this expression in the integral relation reported on top, we again obtain under the partial approximation a closed form expression for this wave function. And the common feature of these two expressions, the one for a Gaussian beam and the one for a Gaussian pulse, is that both expressions reveal the diffractive and dispersive nature of these solutions. So a generical cylindrical solution in terms of an arbitrary spectrum, when the spectra are those of Gaussian type, are diffractive and dispersive. So we may ask, what is the source of this diffractive and dispersive nature? And that they have in common both spectra is that the arbitrary spectrum S rho omega is separable in terms of a function that only depends on rho and a function that only depends on the angular frequency omega. And this is why these solutions are diffractive and dispersive. So let's try to define what could mean a non-diffractive and a non-dispersive property for a general solution of this integral relation up here. And we can say that in order to have non-diffractive and non-dispersive property of this generic solution, we want the wave solutions to be invariant under translation when a certain time has passed. And what amount of time? Well, the amount of time that is required to a wave to travel that distance, that is delta z, with a constant velocity, that is the velocity of the wave itself. This property here is enforcing the rigid transport of the wave along a direction that is the z direction, as we set here. And if we apply the Fourier transform on both sides of this relation, we obtain that this equation, the rigid transport of the wave, implies the fulfillment of the following constraint. Basically, the angular frequency variable needs to have a linear coupling with the spectral variable kz, or maybe it has to be a quasi-linear function, a fine transformation of the variable. And this constraint means that in order to have a localized wave that is non-diffracting and non-dispersive, the spectrum can no longer be arbitrary, but it should satisfy this sort of spectral coupling. And in the following, we will see some examples of spectrum that fulfill this constraint. And we will start for the simplest one, that are called Bessel beams. So in order to keep things as simple as possible, we have again a Dirac function that sets the monochromatic nature of the beam, and then we have another direct function that enforces this linear coupling between the frequency and the radial wave number, as you can see here, because this the argument of this Dirac function has the radial wave number that is coupled to the free space wave number that is a function of the frequency, and an angular variable that here we have called theta naught, that has an important role in the property of Bessel beam, and that we will call more generally hexagon angle. Okay, when we enforce this spectrum in the integral relation that we used so far, that is the integral representation of a generic solution of the wave equation in a cylindrical reference frame, we have that this spectrum inserted in this integral relation gives this closed form expression for the wave function that is basically a propagating Bessel beam with an hexagon angle theta naught. And it can be seen that this Bessel beam solution is equivalent to a spectral superposition of plane waves with wave numbers that lie on the surface of a cone with the angle given by the hexagon angle. And this can be understood by looking at the argument of this Dirac function. Indeed, this integral will give you contribution only when the radial wave number is fixed to this value of Q naught sin theta 0 that fixes the radial wave number to lie on this cone. This is also due for the azimuthal symmetry properties that we enforced here. And the interesting property of this solution is that if you take the modulus of this expression, you can simply see that this solution is invariant with respect to the z-axis. There is no longer dependence from the z-axis. And this is a way to understand the non-diffractive nature of this beam. But now one should ask, how far can we go in the longitudinal direction? Is it really that this beam can propagate along the z-axis up to infinity? This is what this expression is telling us, because it is an ideal expression, but in a real world, this does not happen. Indeed, the non-diffractive properties of Bessel beams are obtained assuming an infinite aperture distribution. However, in practice, you will never be able to generate a beam with an infinite aperture. So the reason why with an infinite aperture you have a beam that is invariant up to an infinite distance can be interpreted, can be understood looking at the reinterpretation of radiation from the fields. Indeed, as I said in the previous slides, in the first slides, interpretation of radiation from an aperture by making a connection between plane waves and rays. As I said, a Bessel beam is a superposition of plane waves that propagate along the surface of a cone. So we can imagine that if we have an aperture, we will have plane waves and then rays that propagate towards the axis of propagation at an angle theta 0. So if we have these rays coming from an infinite aperture distribution, it is easy to understand that these rays will have constructive interference along the z-axis up to infinity, because over an infinite distance, you will always have a ray that impinges on this z-axis. However, if the aperture is truncated, of course, the last emitting rays from the aperture fixes the maximum distance that can be achieved when these rays beat one another in a constructive way. And this geometric interpretation actually gives an approximate formula for the non-diffractive range of a Bessel beam generated by truncated aperture that has a radius that is here called with the symbol rho sub AP, that stands for aperture. And another interesting property of Bessel beams is that this term that is called hexagon angle is also associated to the transverse spot sides of the Bessel beams by this relation here. And basically you have that the ratio between the beam sides and the non-diffractive range, that is a sort of figure of merit that you want to minimize as much as possible, because you would like to have the smallest beam as possible that reaches the farthest distance as possible, is a function of the hexagon angle that goes as the secant of this hexagon angle. So in principle, you will have an hexagon angle that is small as possible in order to minimize this expression and go as far as possible. And of course, the larger is the aperture, the minimum is this figure of merit. So another desirable parameter is to have an aperture that is the largest possible in terms of wavelength. Okay, but now let's see how many ways we have to generate a Bessel beam, because in the previous slide I have shown that we have rays that are emitting towards the center of the structure. But is this really possible? Well, when you have, for example, a cavity and you excite it from the bottom with a simple source, you will have waves that propagate in the outward direction, and in a cylindrical reference frame this will be Hankel function of the secant species and order 0, for example. And since you have outward Hankel function, you will have rays that propagates outward from the source, and then you will not be able to focus energy towards the axis of symmetry. But if you enforce a reflection boundary at the edge of this cavity, you will have also reflected rays that now is an Hankel function of the first species. And the superposition of these two Hankel functions will give you a triangular shaped region where you have a constructive interference of rays and then the generation of a Bessel beam in this region. On the other hand, you have also another possibility to generate Bessel beam from an aperture, and this requires you to have inward Hankel function distribution over the aperture, and we will see next how it is possible in practice to have an inward Hankel aperture distribution in a realistic device. Indeed, if you have only inward Hankel function and you have inward rays emitting from this aperture, you will have that when these rays traverse the axis of symmetry, they switch their behavior from an inward character to an outward character when seen from the other side. And as a consequence, the region where you have a constructive interference of these rays and as a consequence a stationary solution that is a Bessel beam is now this diamond-shaped region instead of this triangular-shaped region that I have shown before. So basically, two ways to create Bessel beams with realistic device, one based on resonant apertures and one based on traveling wave apertures here. Here is a sort of review of some of the progress that has been made for generating Bessel beams, but I don't want to spend much time on this slide. You will. I want just to emphasize that Bessel beams were first discovered in optics, and as you can see, the first realizations with annular slits or hexagon angles resort back to date back to the early 90s or the end of the 80s, while the early generation in the microwave range date back just to less than 10 years ago. And the main reason why there is this temporal gap in this experiment is due to the fact that Bessel beams were generated under the partial approximation that had to be met at microwave frequencies. So let's see an example of a Bessel beam launcher that is a device that is capable to generate Bessel beams by means of a resonant cavity. In order to generate such Bessel beams, we can basically have a circular cavity that has a reflection at the boundary realized by a metallic circular rim. And in order to allow for radiation, we have to put on top of this cavity a partially refracting strain that allows for radiation. We can model this structure with the transverse equivalent network, and we can show that this structure is actually capable of generating Bessel beams, as is shown here, where you can see the measurements of this device that has been fabricated in Rennes, in the University of Rennes, some years ago. And here you have some pictures of the near field measurement setup. And these fields are actually measurements of the fields, and you can recognize the annular shape behavior of the Bessel beams when looked from the top, and the non-diffracting behavior of the beam when looked from a front plane. Okay, let's now switch to the part that is related to X waves. So as we have seen before, basically X waves are the polychromatic version of Bessel beams. So if you allow the frequency spectrum to no longer to be a direct function, but more complex distribution, you obtain an X-shaped pulse generally, if this spectrum is everything but a direct function. And this is basically can be put as a frequency weight that you have over the frequency for Bessel beams. And if the choice to have an exponential taper of the weight of this frequency spectrum with the ordinary active. And actually, if you use this kind of spectrum in this expression, you are also able to have a closed form expression for this ordinary X wave. However, actually, X-shaped X waves regardless of the type of frequency spectrum. So whatever the here, you always call the solution an X wave. Any spectrum provided that is not a direct function, otherwise we will call it a Bessel beam. Okay, the interesting property of an X wave with respect to the Bessel beam solution is that it is not only focused along the transverse direction, but also along the longitudinal direction, the z-axis. That is the axis where property. And in particular, it's interesting to note that if you assume to have the simplest frequency spectrum that you can imagine, that is a window function with an extension that gives the bandwidth of the spectrum, that basically uniform frequency speed constant, or say over bandwidth delta omega and zero elsewhere, you are not able to find a term expression for the entire equation, but you are able to find simple expression to evaluate the longitudinal spot size that is reported here, and tells you that the longitudinal spot size is inversely proportional to the fractional bandwidth. This is a very interesting property because it means that in principle you can squeeze the beam along the longitudinal z-axis as much as you want if you enlarge the fractional bandwidth of the poles. And the other interesting property is that the transverse spot size of an X wave is inherited from Bessel beams, is the same expression that you have for Bessel beams, and this can also be inferred from the fact that actually the X wave solution is basically a weighted spectral superposition of Bessel beams that share the same hexagon angle. Well, now let's see what we need to do in order to define better the property of X waves. Indeed, since an X wave is localized on both the radial and the longitudinal direction, you could define a sort of localization in a two-dimensional localization along the z-axis and localization along the transverse axis. With respect to the transverse axis, you can define simply a figure of merit, that is how much the beam is large with respect to diameter. But what about the longitudinal axis? Well, the most common way to define a sort of figure of merit on the longitudinal axis is to compare the longitudinal spot size with respect to the non-diffractive range, because beyond the non-diffractive range, the pulse will no longer be confined. And this brings us to define these confinement ratios, that are basically the ratio between the transverse spot size and aperture diameter and the longitudinal spot size divided by the non-diffractive range. Since we have approximate analytical expression for these variables, we are also able to give analytical expressions for these confinement ratios. And in order to have a single figure of merit, we can combine this confinement ratio in a single figure of merit that we call 0Z, that is said to be the product of these two confinement ratio, and we can say that is 1 when that the maximum of these two confinement is greater than 1. That means if the pulse is not confined in one of the two directions, at this point the wave is no longer confined. So it has to be confined along both directions in order to say that is confined. And if we report this figure of merit in a contour plot where we have this figure of merit function of the aperture size on the x-axis and the hexagon angle on the y-axis, we obtain this figure that shows the boundaries where we can say that the beam is the pulse is confined or not confined. The brighter the color, the more confined will be the pulse. In the dark region, the outcome either is not confined along the radial direction or the longitudinal direction, or even both directions. Examples of this is provided here. If you generate a pulse with an aperture radius of about 20 from an hexagon angle of 20 degrees, you have this pencil-like X wave that is extremely confined on both directions. If you move here where the color starts to get darker but is still in the confined region, you still have a beam that is confined but is a little bit broader than the previous one. If you place your pulse with parameters in this region, it will be confined only along the longitude, only along the transverse direction, but not confined along the longitudinal one. Here in this quadrant here, it will be confined only along the longitudinal direction, but not the radial one. And finally here, it will no longer be confined along both directions. So you will say that you don't have an efficient X wave, that is not useful for applications. However, all these results have been obtained assuming that the fractional bandwidth is about 20%. But what is the effect of the diffraction bandwidth? Well, if we assume to have almost a Bessel beam, let's say a fractional bandwidth of just 1%, you can see that when we evaluate the figure of merit, that is only a very narrow region where you can get confinement, because a Bessel beam is confined only along the transverse direction, as you can see here. So you cannot say that the pulse is confined because you have confinement only along the radial direction, but it's almost constant along the z direction. But if you start to increase the fractional bandwidth, what happens is, as I said in the first slides about the property of X, you will squeeze the pulse along the longitudinal direction. And this is what is represented by the animation here. But you can see that after a given point, a point is reached where there are not much differences on the X-ray, so there is no point in having such a large fractional bandwidth of the poles because their property are not affected much after a certain point that we said is about 20, 30. Okay, one thing that I should point out at this stage is that all these assuming an ideal X waves where the X-econ angle does not change with frequency. That is called a non-dispersive ideal X waves. However, especially when we try to generate this wave at microwave frequency, wave number frequency dispersion has not to be kept. And if we assume that there could be a wave number frequency dispersion affect also the X-econ angle by means of this relation has, and then we will have cone dispersion that will cause the pulse some dispersion along propagation. However, it can be proven that if this dispersion is not much prominent, and you fall in a so-called weakly dispersive case, you can still be able to have an almost focused X waves that maintains its non-diffractive property along propagation. This is the story of X waves as for Bessel beams, and basically there is the same epilogue, I would say, where you have the early realizations in optics that occurred in the 90s, while it has been more X waves just few years ago. The experiment of X waves at microwave frequency occurred. First one by the group of Tony Gerbich in Michigan in 2018, and few years later by me and Dr. Coit in 2018 here with the help of Professor Burghignoli, Professor and Alessandro Galli, and Simon Podilchak, a colleague of us that is in University of Edinburgh, that a great contribution for the experimental validation of this device. And here I just want to show techniques to generate X waves because as you can imagine, you can no longer use resonant aperture because you need to have a considerable fractional bandwidth to have an efficient pulse. So you can only resort to aperture that are have two ways to generate such apertures. One can be done by using radial line slot arrays, and is to use an autoidentical wave distribution but excite a backward periodic aperture. I don't have time to give much details about the have a backward wave by exciting an aperture with a simple source that excite outward angle wave, but this can be done by means of the leaky wave interpretation of radiation from the structure. So basically you have these two ways to generate X waves with traveling wave aperture distribution, and you can I can skip this slide that talks about the property of both RLSA and the leaky periodic out of time. I want to show you an animation that shows you how you can actually design one of these devices. Basically, you have you fix some design parameters such as the operating frequency, the aperture size, the X-econ angle, the maximum dispersion of the X-econ angle that you want within the bandwidth that here is fixed to a fractional bandwidth of 20%. And as a consequence, you will have a non-diffractive range that here is dictated by this choice to be on the order of 120 wavelengths. Well, this choice put you in this plot just here, and as I said, this is the plot of the confinement figure of merit that is telling us that we are expecting to have a very confined X wave. And indeed, if we look at the along the frequency domain, we can see that as the frequency is changing, you have of different property that have been generated along the frequency, and since the beam is changing a little bit its shape, we can expect that we will have some dispersion in the generation of the X wave. This is actually what we obtain. You can see that as long as the pulse is traveling within the non-diffractive range, it maintains its shape. But when it goes beyond this distance, it starts to spread and to decrease its amplitude because of energy conservation. So this concludes my presentation. I hope you enjoyed it. I have talked a little bit about the connection between plane waves and rays to give a geometrical ray optics interpretation of the radiation from aperture, and this gave me opportunity to talk about diffractive beams of the Gaussian type and non-diffractive beams with specific attention that can have a lot of application in the microwave range thanks to the focused and non-diffractive character. So thank you for your attention. Here you can find some references if you are interested to have more details about what has been discussed in this seminar. And if you have any question, please do not hesitate to ask now or to write me an email. Thank you.
Hello, this is Andris Stoya from non-Diffracting. I just have a question regarding this Bessel beam launchers.
Okay, so I thank again Dr. Fuscaldo for this very interesting seminar. The slides will be made available in PDF format on the website of the course. And I will send you an email in the next few days in order to ask you for some feedback about this course. Yes, I think that Andris Stoya is asking me if I can share your email. I think I will send it to you.
Yeah, you could say that it's just name or .surname.
Okay. IT. Anyway, I will write it also in my email message. And I will give you some information about the way to, let's say, pass the exam. It is not actually PhD students. This year, differently from the previous years, I think that I will ask you to prepare one topic taken from this course and to expose it orally, most probably at a distance, whenever you. That is in order to get the credits necessary for your PhD course. Okay, so I thank you again very much for your attention, and see you soon and in any later occasion. So bye and see you.
Thank you. Bye.
Grazie mille, professore. Buona giornata.